Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 3.23. Problem statement says, a mixture of methane and air is capable of being ignited only if the mole percent of methane is between 5% and 15%. A mixture containing 9 mole percent methane in air flowing at a rate of 700 kilograms per hour is to be diluted with pure air to reduce the methane concentration to the lower flammability limit. Calculate the required flow rate of air in moles per hour and the percent by mass of oxygen in the product gas. Note, air may be taken to consist of 21 mole percent oxygen and 79% nitrogen, and to have an average molecular weight of 29.0. Let's go ahead and start writing down what we know. We've got our mixing unit here. We've got one stream going in. Stream number 1 has a mass flow rate, and the mass flow rate equals per hour. And they told us that the mole fraction of methane is equal to 9, and we know that we've got a certain amount of air in here. That's all the makeup. So 91, stream number 1. Then we've got stream number 2 going in, and stream number 2 has a mass flow rate, but we don't know what it is, and it's all air. Then we've got a certain product stream going out. That is stream number 3. It has a certain mass flow rate that's equal to mass 1 plus mass flow rate 2. It said that we need to reduce this mass flow rate to the lower limit, which is 0.05 mole fraction. So XM3 needs to be at least this much, which means that the rest is air. And what else do we know? They want us to determine molar flow rate of stream 2, and they also want us to know how much weight fraction is oxygen in the product stream. So weight fraction of oxygen in the product stream. Those are the two things we need to find out. Okay, and then they gave us that in air, and then they also gave us the molar mass of air. 29. What are we working on? We're in kilograms. Let's do kilograms per meter cubed. Nope. Per kilomole. Okay. We have 3 ingredients in this stream, in these streams. We've got methane, oxygen, and nitrogen. Okay, and so we'll also need to be converting between moles and mass of all of these ingredients. So let's go ahead and look up these ingredients: molar mass of methane, molar mass of oxygen, molar mass of nitrogen. And the units are all the same. Okay, so we've got all the molar masses. So let's start doing mass balances on all these streams for each component. Okay, so how much methanol do we have going in stream 1? Okay, so let's look at stream 1. We've got certain mole percents, and a mass flow rate. We convert mass flow rate into mole flow rate. We can if we know the average molecular weight of that stream. So let's add up the different molecular weights that we know. We can get that from the mole ratios that they gave us here. We can calculate an average molecular weight for this stream. Oops, I just saw I made a mistake here, that I wrote a 2 subscript on the stream 1 properties, so sorry about that. We're changing those back to 1s. Okay, you do the sum product of those things, so they're weighted by their molecular weights. Okay, so the average molar mass of stream 1 is 27.83 kilograms per kilomole. Okay, so now we can calculate what the molar flow rate is for stream 1. So the molar flow rate for stream 1 is equal to the mass flow rate of stream 1 divided by the average molecular weight of stream 1, which equals per hour, because we started off with 700 kilograms per hour, and we know the molar mass of the average molar mass of that stream. Okay, so what are we going to do with this? We're doing mole balances on the different components. Okay, so now we can split these moles up into our different ingredients here. So we've got methane. How much methane is going into our mixer unit, our box right here? How much methane is going in to this box, and how much methane is going out? We can do a mass balance. Okay, so methane balance, how much is going in? Well, we have the molar flow rate of stream 1 times the mole fraction of how much methane is going in. And then how much do we have coming out? Well, we have the mole flow rate of stream 3 times the mole fraction of stream 3 coming out, okay, which is 0.05. Okay, so that is minus how much is going out, and that should equal 0 because there's nothing accumulating inside of this box. There's no mass or any accumulation or generation term or anything like that. So those are the only components that we have. So we know that the amount of methane going in should equal the amount that's going out. And we know this term, and this term, so we can solve for the molar flow rate going out. Okay, so the total molar flow rate going out is equal to 45 hour. Okay. Let's calculate we have enough information now that we can calculate what the total molar flow rate going into stream 2 is, because we know our overall mass balance is the moles. So we've got N3 should equal N1 plus N2. Okay, so N2 equals N3 minus N1, and that equals 20.12 kilomoles per hour. That is the answer, one of the answers that we're looking for. Now we need to do an oxygen balance and find out the mass fraction of oxygen in the product stream. Okay, so let's start balancing our oxygen. Oxygen balance, a certain amount of oxygen in stream 1, and that should equal 0 because there's no accumulation, generation, or anything like that. Okay. Okay, so we know most of these terms, but we don't have enough information as of right now to calculate how much oxygen here and how much oxygen here. Okay, so let's do another quick look at a quick breakdown on stream 1. So we know how much air is going in. So how about we look at how much air is going in, and then if we get like an airflow rate in stream 1, then we can break that up using this information that they gave to us. So let's do that. Let's break up how much air is going in stream 1. Okay, so in stream 1, let's do that over here. We're returning to stream 1, and we're doing an air balance. We know in stream 1 that we have 25.15 kilomoles total. So we have a certain flow rate going in. And we know that a certain fraction of that is air. So the 0.91 fraction of that is air. So that means that we now have a molar flow rate of air in stream 1. Okay, if we know how much air is going in stream 1, then we can further break that up using our air information here. Okay, so let's figure out how much oxygen and nitrogen are in there. We know that 0.21 fraction of that air stream is equal to the amount of oxygen flowing in stream 1. And then we know that the rest is the nitrogen. Okay, and then if we have the mass flow rate of oxygen and nitrogen and methane, then we can figure out what the total molar fraction is of oxygen. Okay, so let's calculate what those are. 2.26 kilomoles per hour of methane going in. Okay, so now we can get our overall mass fraction of oxygen going into stream 1. So our overall mass fractions. Okay, now we've got our overall mass fraction here for stream 1. And that was the really important one, because now that we have that, we have our last remaining mole fraction for stream 1 that we needed to know. So now we can calculate how much our mole fraction is in, how much oxygen mole fraction there is in stream 3. Okay, so let's calculate that from our other oxygen mass balance. Our total mass fraction of oxygen, or our total mole fraction of oxygen in the outgoing stream, we need to turn this mole fraction into a mass fraction. And in order to do that, we need to calculate the average molecular weight of the outgoing stream so that we can convert this molar flow rate into a mass flow rate. Okay, So in order to do that, we need to know the mole fraction of each component in stream 3. Okay, so now we have the different components. We can figure out the average molecular weight of stream 3 by doing a weighted average. Of the different components in stream 3 and using their molar masses. And doing that, we get so now we have the average molar mass of stream 3. We can convert our molar mass into a mass flow rate, then convert our moles of oxygen in stream 3 into a mass flow rate, and then when we have the two different masses, the total mass and the mass of oxygen, then we can calculate what the mass fraction is of oxygen in stream 3. And they asked for the weight fraction of, they asked for the percent by mass of oxygen. So we have the weight fraction of oxygen. So in order to get percent mass of oxygen is 23%. Okay. All right, so that is it for problem number 3.23. We've solved both of the things that they asked for here. We got our molar flow rate of air into the mixer, and we have the mass percent of oxygen in the product stream. All right. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.